Right now, somewhere in your house, there's a metal box trying to exhale like gallons of moisture into the atmosphere.
Yeah, and if that airway gets blocked, it doesn't cough.
Right.
It doesn't wheeze to tell you it's struggling.
Exactly. It just gets hotter and it works harder until something eventually breaks.
Right, which is why checking if your clothes dryer is actually pushing air out is quite literally like checking a patient's breathing.
But how do you actually, measure the lung capacity of an appliance?
It is a massive mechanical challenge
Yeah.
because you aren't just dealing with the machine itself. I mean, you are dealing with airflow, heavy moisture, lint.
Yeah, and that totally hidden labyrinth of ductwork in your walls.
Exactly. Buried in crawl spaces or ceilings, you can't just look at a dryer, press start, and say, yep, it's healthy.
Which brings us to the core mission of our deep dive today. We're exploring this fascinating diagnostic methodology, the Dryer Vent Safety Council, or DVSC negative pressure measurement method. We have the official DVSC technical publication here, plus some really incredible historical development notes.
Yeah, the history is super interesting.
It really is. So our goal for you today is to decode exactly how this testing method works, the fluid dynamics behind it, and why engineers developed it in the first place.
But before we dive into the actual science of negative pressure, we really have to draw a firm line in the sand about how this method exists out in the real world.
Okay, let's unpack this because context is everything here.
Right.
If you are a technician or just trying to understand the industry, you have to look at this through the concept of a diagnostic toolbox.
Precisely. The absolute most critical piece of context for you to understand today is that the DVSC negative pressure measurement method is just one of multiple methods used to evaluate clothes dryer exhaust systems.
Right, it's not the only way.
No, it is absolutely not a standard.
Yeah.
It is not the exclusive, it's not the preferred, and it's not the definitive way to test a dryer. I want to be incredibly clear on this point.
Go ahead.
This is another tool available to technicians for evaluating dryer exhaust performance.
Okay, so it's an option.
Exactly. Rather than replacing airflow or back pressure testing, this method provides an additional way to evaluate system performance by measuring negative pressure inside the dryer.
Let's ground that in reality for a second. Out in the field, technicians have this whole array of approaches, right?
Oh, absolutely.
Like a very common method is using an anemometer to measure airflow velocity right at the exterior termination.
Right, basically standing outside the house and measuring the air blowing out of the wall vent.
Yeah, or up on the roof. And another really common one is measuring back pressure in the duct right behind the dryer using things like a Magnehelic gauge.
Yeah, exactly.
And of course, whatever specific testing requirements the manufacturer outlines, well, those always take precedence over anything else.
Always.
So the negative pressure measurement method is the principal subject of our deep dive today, solely because we are taking the time to explain its specific mechanics, not because it's endorsed above those other methods.
That is a vital distinction. The appropriate measurement method always depends on the specific dryer, manufacturer requirements, field conditions, and, well, the purpose of the test.
Right.
The DVSC publishing this just means they've documented a highly repeatable procedure and gave guidance on interpreting results. Nothing more.
So keeping that toolbox context in mind, let's get into the history. Because measuring a vacuum, which is what negative pressure is, seems kind of counterintuitive.
It does, yeah.
A dryer's whole job is to blow air out. Why would someone decide to check a blower by measuring a vacuum inside the drum? What were people doing before this?
Well, to understand that paradigm shift, you have to picture the old reality of the job. Technicians were kind of flying blind unless they physically got to the end of the line.
Which means the roof.
Right. Pulling out a 30-foot ladder in the middle of winter, climbing onto an icy roof, and sticking an anemometer into the exterior vent just to get a baseline reading.
That sounds completely miserable.
It was dangerous, time-consuming, and really inefficient.
So who changed the game?
A brilliant engineer and vacuum measurement developer named Gregory Newman.
Okay.
He is a named inventor of an important predecessor device called the Whirlpool Airflow Tester, W10106710. Newman essentially applied a fundamental fluid dynamics principle to appliances.
And what was that concept?
Basically, what if we evaluate the total airflow performance by measuring the vacuum, the negative pressure, created within the dryer drum itself?
I want to stop and make sure we really grasp this because it's brilliant lateral thinking.
Yeah, it really is.
If you're listening to this, maybe while you're folding laundry, think about what's happening in that machine. The blower wheel acts like a pump, furiously trying to evacuate air and push it out the back.
Right.
So imagine trying to drink a really thick milkshake through a very thin straw. The harder you pull, the more your cheeks cave in.
Exactly.
That caving in is negative pressure. If a dryer vent is clogged, that's the thin straw. The blower is still pushing, but because of the downstream resistance, it creates a stronger vacuum upstream right inside the drum.
That milkshake analogy is spot on. The drum is the mouth, the vent is the straw. Newman tested this across numerous dryers and established an essential minimum performance reference point of approximately 0.10 inches of water column.
Wait, hold on. Inches of water column. We hear this jargon in HVAC all the time, but what is it literally?
Oh, historically, it's exactly what it sounds like. Before digital sensors, engineers measured low pressure using a simple glass U-shaped tube, partially filled with water.
Okay, so actual water.
Yeah. One end is exposed to the pressure you're measuring, the other is open to the room. The pressure literally pushes the water down on one side and up on the other.
And you just measure the difference.
Yep, you take a ruler and measure the difference in inches. So 0.10 inches of water column means the vacuum is strong enough to pull that water a tenth of an inch.
Which is tiny, but it's incredibly revealing. It's like having a doctor check your lung capacity right at your mouth instead of crawling through your respiratory system.
Exactly. It was a massive leap forward. The Whirlpool tester proved you could accurately classify dryer performance right there in the laundry room, bypassing the immediate need to climb a roof.
But the industry didn't stop at the Whirlpool tester, right? Because according to these notes, that specific proprietary tester was discontinued?
Yeah, it is no longer commercially available.
That must have caused panic for technicians who used that approach.
It definitely left a significant gap in the toolbox. But the DVSC realized they didn't need to replicate the physical device itself.
Right.
They could establish an independent, pressure-based test method using commercially available off-the-shelf equipment.
So what did they use?
They built a practical, highly repeatable field method utilizing a standard dual-port digital manometer.
And a digital manometer, for anyone unfamiliar, is essentially the modern digital version of that U-shaped tube of water.
Yep, exactly. It has two ports and measures the difference in pressure between Zone A and Zone B.
In this case, the negative pressure inside the drum versus the ambient room air. But to connect that manometer to the drum, the DVSC designed a very specific assembly. And reading this publication, it is hyper-specific.
Oh, absolutely.
They call for standard silicone pressure tubing, but then a very specific probe tube. A McMaster-Carr crack-resistant PFA semi-clear tube, 1/16th inch inner diameter, cut precisely to 12 inches.
Yes, very precise.
If I'm a technician, why can't I just use whatever spare plastic hose I have rolling around my van?
Because if you do that, the test becomes scientifically invalid. This is a standardized field procedure. If Technician A uses a thick rubber hose and Technician B uses a thin plastic straw, their manometers will read differently on the exact same dryer.
Okay, you have to control the variables.
Exactly.
But I have to push back on another detail. The guide explicitly says you must cut this 12-inch tube using a knife and absolutely not with shears or scissors. Is that just being pedantic?
It isn't pedantic at all. It is pure fluid dynamics.
Right.
Think about the mechanical action of scissors. They work by crushing two sides of a material together before cutting it. If you use shears on a tiny tube, you permanently pinch and deform the opening.
Ah, I see. You create an artificial bottleneck.
Exactly. That crushed tip introduces a micro-restriction right at the intake. That tiny bit of artificial friction changes how air enters, which artificially skews the manometer reading.
So it might falsely lead a technician to believe the system is clogged.
Precisely. Cutting it with a sharp knife preserves the perfectly round geometry. And to get a tight seal between that pristine probe and the silicone tubing, you use a short piece of automotive silicone vacuum hose as a friction fit adapter.
Okay, the fluid dynamics of a clean cut makes perfect sense. So the technician builds this assembly, they make sure the dryer is completely empty, lint screen totally clean.
Right, no stray socks messing up the baseline airflow.
Here's where it gets really interesting though. The guide says they insert this rigid 12-inch probe exactly 2 inches into the upper interior of the drum, through the rubber door seal, close the door, and run the machine for 60 seconds.
That's the procedure.
Won't a plastic probe sticking into a spinning drum get absolutely smashed by the laundry paddles?
That is a critical mechanical observation, and the DVSC method accounts for this explicitly. This method is specifically intended for conventional front-loading residential clothes dryers.
Ah, okay.
In a standard front loader, the upper interior space near the door seal remains clear of the tumbling mechanics. The tube sits safely in dead space.
But not all dryers are conventional front loaders.
Exactly. And this is a massive caveat. There are certain specialty top-loading tumble dryers, specifically select Fisher and Paykel and ASCO models, that are fundamentally incompatible with this test.
Because their drums rotate entirely differently, and the drum would just strike the probe like a baseball bat.
Correct. Attempting this on those machines could damage the appliance or the equipment, which loops back to our very first point. Manufacturer model-specific requirements always take precedence.
So if a tech sees one of those, they don't force it. They pull out a different tool, like a magnehelic gauge.
Exactly. Just use a different method.
So assuming we have a compatible front loader, the technician zeroes out the manometer, sets it to max mode, and runs the dryer on air only, or FLUFF strictly, no heat, for a minimum of 60 seconds.
Right, to let the airflow stabilize and capture the highest sustained negative pressure.
They look at the screen. What number are they looking at? Because the industry uses inches of water column, but this DVSC method specifically uses pascals, abbreviated as PAS.
Right, and what's fascinating here is the rationale behind shifting to pascals. You have to evaluate this from the perspective of human factors engineering.
Oh, so.
The goal wasn't laboratory-grade granular precision. The goal was a foolproof, simple, repeatable field, diagnostic for humans in difficult environments. Digital manometers generally display pascals directly in clean, whole numbers.
And 1 inch of water column equals roughly 249 pascals, so it offers drastically finer resolution. But, playing devil's advocate here,
Right.
the notes mention if they used kilopascals, or kPa, readings would look like 0.013 kPa. Instead, in pascals, it's just 13. Is reading a decimal really that big of a hurdle for a trained professional? Are we dumbing down the math?
I understand why it might look that way, but it absolutely is not about dumbing things down or questioning anyone's intelligence. It is entirely about cognitive load and mitigating environmental friction.
Like in other high-stress jobs.
Yes, we see this in aviation and medicine all the time. Anesthesiologists use whole number integers for certain drugs to prevent fatal transcription errors.
Okay, a dryer isn't an airplane, but I see the parallel.
It is the same psychological principle. Put yourself in the technician's boots. You are not in a brightly lit lab. You might be wedged behind a washer-dryer stack in a dark, unair-conditioned laundry closet.
Yeah, that's true.
You're holding a flashlight in your teeth, crouching at an awkward angle, reading a dusty screen, and taking notes on your knee.
All right, painting that picture, a 0.013 is dangerously easy to misread as 0.13.
Exactly. A misplaced decimal point in a field report could mean the difference between diagnosing a catastrophic fire hazard and giving a dangerous system a clean bill of health.
Wow, okay.
Under those real-world conditions, recording a clean integer like 13 or 27 is vastly superior. It creates an intuitive, error-free field reference scale.
That completely flips my perspective. It's about practical usability. So the technician has this whole number in pascals. How do they know what it actually means?
They didn't just guess in a laboratory.
Right.
The DVSC conducted extensive real-world field testing and correlation work to translate this into actionable data.
Right.
He took these manometers into more than 100 unique residential field locations.
And that's crucial because a lab doesn't have crushed transition ducts or illegal 90-degree elbows or 10 years of pet hair.
Precisely. They needed a data curve reflecting the chaos of actual houses.
Okay.
By correlating these real-world readings, they established highly practical performance bands.
And they turn this into a traffic light classification guide, right?
They did. It breaks the Pascal readings down into 3 authoritative thresholds.
Let's walk through those thresholds. First, green. That means adequate airflow. If it reads 25 pascals or higher, the system is performing as it should.
Correct. No severe restrictions.
Then yellow, marginal airflow. That's between 13 and 24 pascals. It indicates a partial restriction, starting to struggle, should be cleaned.
Exactly. It's a warning zone.
And finally, red, restricted airflow, 12 pascals or lower. That is a severe restriction. The vacuum has collapsed, and it absolutely must be cleaned.
Those numbers, 12 or below for red, 13 to 24 for yellow, 25 or above for green, are the finalized criteria of the DVSC publication. They let a tech quickly and confidently classify the system's condition.
So what does this all mean? Looking at this journey, from Gregory Newman to the modern manometer, the most powerful aspect to me is the holistic nature of the test.
How do you mean?
It intentionally evaluates the entire system as installed from a single point. because
Mhm.
that reading inside the drum is fighting the combined resistance of everything. The dryer, the internal ducting, the transition duct, the wall exhaust, the exterior roof vent, it captures the total drag.
If we connect this to the bigger picture, you just highlighted the exact philosophy of this measurement method. It evaluates the system as a single working unit.
Right.
It allows the tech to take a baseline reading, perform a vent cleaning, and run the exact same test again. If they started in the red at 10 pascals and finished in the green at 30 pascals, they have tangible, objective proof for the homeowner that airflow is restored.
It takes invisible air, measures its struggle, and turns it into a clear whole number. A fantastic addition to the diagnostic toolbox.
It really is.
But as we established at the very beginning, it remains just one tool in that box.
It does. But analyzing how this specific tool works, how it captures the entire system's resistance from inside the drum, this raises an important question, and this is something for everyone listening to really think about.
Okay, what is it?
Let's say a tech runs this test and gets a red, restricted reading of 8 pascals. They go into the walls, up on the roof, and perfectly clean every inch of the household ductwork.
Spotless.
Spotless. They run the test again, and the manometer still reads 8 pascals, still red.
Wait, the house ductwork is totally clean, but the system is still choking.
Exactly. Because this single interior test point measures everything downstream, it forces us to realize something people forget. The dryer appliance itself and its own internal ductwork is a major part of the exhaust system.
Oh, wow.
If the wall vents are clean but the reading is restricted, it reveals the dangerous clog isn't in the house's architecture at all.
The call is coming from inside the house, literally inside the appliance.
Yes. The blockage, the severe fire hazard, is buried deep inside the very machine you trust to dry your clothes. You might spend hundreds cleaning wall vents, totally unaware the machine itself is choked off internally.
That is a genuinely chilling thought. And it brings us right back to our hook. We assume our everyday machines are breathing fine. But until a technician utilizes the right tool to measure it, you might never know the lungs of the machine itself are failing.
Exactly.
Well, thank you for joining us on this deep dive into the DVSC negative pressure measurement method. Whether you are a seasoned technician or just someone doing a load of towels, keep questioning how the everyday systems around you actually function. We'll catch you next time.